Hello. Yes, we welcome you back to PSSB, uh, Physical Sciences Silver Bullet. It's me, Richard, once again. Today we are looking at this question. It comes from the red. Okay, let's check what we have here. It says that in an experiment below, dilute acids are reacted with excess zinc in 3 different experiments. For each experiment, 1.6 grams of zinc was used. So these are the 3. This is the first one where we are using 100 cubic centimeter of this concentration. Then we have the second one, the third one. And here it says that the volume of gas liberated is plotted against time, and the graph below is plotted for experiment 1. Okay. Then comes the question 13.1. It says, at what time T1, T2, and T3 is the reaction fastest? Okay. So when you look at this scenario, this is what you have to know. That rate of reaction is proportional to the concentration of the reactant. And what do we notice? That as time passes, the amount of reactants tends to decrease because it's being used up. And it is on that basis that we say that rate of reaction decreases as time passes. So for that aspect, you can say that the rate of reaction at T1 is higher than that of at T2, and the rate of reaction at T2 is higher than the rate of reaction at T3. So on answering this question, what's the answer? Because the question says, at what time is the reaction fastest? The answer is T1. Thank you. Then comes this question, 13.1.2. It says, at what time is the reaction slowest? We'll have to go back to the same explanation we gave before. Rate of reaction is proportional to the amount of reactants available. But you have to know that as time passes, the reactants are being used up, so that they tend to decrease. So that time is going to be T3, because at T3, most, if not all, the reactants are used up. So the answer is T3. Yeah, then comes this question, 13.2. It says, at what time is the amount of zinc present smallest? Okay, this one we go back to the same explanation we gave before. What happens when 2 entities are put together to react, or 2 reactants are put together to react? They react. So as they react, what happens? They decrease in amount because they are reacting to form the products. So under that circumstance, the amount tends to decrease. So the amount of the reactants at T1 is more than the amount of reactants at T2, and the amount of reactants at T2 is more than the amount of reactants at T3. Zinc being one of the reactants, it is smallest at T3 because a lot of time has passed. So a lot of it has decomposed. Thank you. Then comes this question. Um, um, it says that at what time is the amount of zinc present the biggest? It's the same explanation. As time passes, the amount of reactants tends to decrease because they are reacting. So when you compare the 3 times, the T1, the T2, and the T3, we are going to conclude that at T1, the amount of reactants is bigger compared to the preceding one. So at what time is the biggest? It's going to be T1. Thank you. So that is that. Yeah, then comes this question 13.3. It says, what does each below represent? Okay, so volume V. Volume V is this one here. And what does that volume represent? It represents the volume of gas liberated during the experiment. Or it's also acceptable to say it represents the total volume of gas liberated during the experiment. Let me take you somewhere here. At T naught, the reaction is just starting. The particles are coming together to react. So as we progress, what do we see? The volume of gas increases. It increases and increases. And at this point, what happens? The graph flattens. What does that mean? That no more gas is being given out. No more gas is being liberated. So, in other words, V represents the total volume of gas liberated or released during the experiment. Then comes another question. It says, what does time T3 represent? Okay. Okay, T3 is this one. What is indicative of T3? Volume of gas is being liberated, it proceeds going on increasing. What happens at T3? The graph flattens. And the flattening of the graph means that no more gas is being liberated. What does that mean? Reaction has stopped. So T3 is the time for the reaction, or time for the reaction from start to the end. Thank you. So that's that. The time for completion of the reaction. Okay. Yeah, then comes this question, 13.4. It says, calculate the mass of zinc present after completion of experiment 3. What we have here is experiment 3. And the acid used in this case is hydrochloric acid. So how do you approach this question? We are going to approach it stoichiometrically. We write the reaction. What's the reaction? We are having zinc reacting with a hydrochloric acid to give you zinc chloride plus hydrogen. Okay. What's the next step? Is to balance. So how do you balance this one? We balance this by putting a 2 here. So the equation of the reaction is now balanced. This one is aqueous. This one is aqueous. And this is a gas. Okay, like what do we do under the circumstance? To make it easier, we look at our major reactants. This side we are going to have zinc, and this side we are going to have HCl. Okay, the ratios are 2 to 1. Okay, now you have to know something. For the rate, this concept must be in your mind, the concept of the limiting reagent. So when you look at this case, they told us that zinc was in excess. So not all zinc was used up. So here it was depicted, you can get it from here. Direct acids are reacted with excess zinc. So, which means that we don't know how much zinc reacted. But at least after knowing that zinc is not the limiting reagent, now we are absolutely clear that hydrochloric acid is the limiting reagent. So it's the one which is our standard. What do we say? We say C that's the concentration is 0.2 moles per cubic decimeter. Okay. What else do we have here? We know the volume. The volume is 100 cubic centimeter, but we convert it to cubic decimeter and you get 0.1 cubic decimeter. When you have concentration and volume, it gives you number of moles reacting. Okay, so you say C is equal to N over V. And when you substitute here, C is 0.2. Number of moles are needed, but we know the volume, which is 0.1. From here, our number of moles can easily be obtained. So after getting the number of moles, what do we say? You come here and say that now we are looking for number of moles of zinc which reacted. Well, let's call it X. And we have to know, we know that this ratio and this one and the number of moles here and our X here. So we are dealing with directly proportional ratios. So what do? This one is going to be multiplied by this and this one with this. So what do we get after that? We are going to say 2x is equal to 0.02. So our x is going to be 0.02 over 2, giving you 0.01. After getting that one, what do? These are moles. And what do they represent? They represent the number of moles of zinc which reacted. So what do? We convert them to mass using a very clear known equation, which says that N is equal to M over molar mass. Okay, which is 0.01, giving you the mass which you are looking for over molar mass of zinc. Let's check for it. Okay. From the periodic table I've checked, we have got it as 65.4. 65.4. And after that, now we can get the mass. Okay. Yes, so the mass of zinc which reacted is 0.654 grams. That's it. So, but remember, this is not what is wanted. It's a route to what is wanted. The question is very clear. It says calculate the mass of zinc present after completion of reaction. After completion of reaction. Is that okay? So in other words, we have what reacted and we know what was supplied, which is 0.6. The difference will give us mass of zinc present in the flask after completion of the reaction. So after a subtraction, this is what we get. 1.6 minus 0.654 gives us 0.946 grams. Okay, so this is the mass of zinc present in the flask after completion of the reaction. So with that, we are going to cut this video here. Another question is going to be in the next video. Yeah, we appreciate your time and we thank you for sticking with us. We would appreciate if you feel our videos are impactful, please click the like button and also refer it to a friend. Thanks very much. Don't forget the channel is PSSB, Physical Sciences Silver Bullet, and it's me, Richard. See you next time. Bye-bye.